Check, check. All right, folks, we're going to start up. Come on down. Very good.
This is my chair.
Well, the first thing I want to say is welcome to Tandy Assembly 2024. It's thrilling to see everyone and welcome everybody, and I get the distinction of being the victim of being the first speaker, so I'm thrilled. My name is Tim Halloran, and I'm going to kind of talk today about using logic analyzers to troubleshoot and understand your TRS-80s. So kind of an outline, I'll do a little bit of an introduction. I'm going to sort of talk about what I'm going to talk about and give some caveats, and then we'll go through what I have, and then we'll kind of circle back to that and talk about it at the end. And then we'll finish up with some questions and discussions. I can't see people too well, so if you're trying to ask a question, you may have to yell. And I'm supposed to repeat the question, so I don't want to forget that. So introduction. The plan of the talk is let's introduce the logic analyzer, and I'm going to contrast it a lot to an oscilloscope, which I'm hoping for most folks might be a little more familiar. This is probably more useful to folks that have never seen this or aren't quite sure what I'm talking about yet than it is if you're like a seasoned pro with this. So a few caveats before we get going. First off, not everyone needs a logic analyzer. So before you go out and buy one of these on your phone after this talk, depending on what you're doing, you may not need this. And it's definitely not the first bit of test equipment if you're trying to fix computers that you should have. First off, a good multimeter is probably a worthwhile investment. And then you probably definitely want an oscilloscope before you have a logic analyzer. Logic analyzer also these days, they can be built into the oscilloscopes. I'll be demonstrating that quite a bit. That's really convenient as well. I didn't put this on here, but the logic analyzer is oftentimes used when you're trying to work on something that's working to expand it or do something new with it, as opposed to, it's not the most useful device for just troubleshooting your Model 1 or your Model 2, trying to figure out how to get it to work. So I did want to caveat that the examples in this talk are a little bit simple. Some of you may be sitting there going, this seems crazy, but oftentimes when you work on a logic analyzer, it comes into its own with very complex logic. You might have 32 signals going, and it can have a lot of them. And when you actually do this, you'll build this up, signal at signal, and in your head you'll have a good abstraction of what's going on. But if I put up something with tons of signals, everybody will be like, what the heck are you doing? So I've tried to simplify these enough that you get the idea, but they're mostly simple examples that everyone can sort of follow. And that's kind of the introduction. So the first example I have is a Coco 1 example. The Coco clock E and Q, and I'll talk about what E and Q is. So we're going to talk about doing this with the oscilloscope. So there's a couple of pins. I think I'm hooked up to the CPU here on the Model 1. On the Coco 1, you can see I've got two probes on the oscilloscope, and I'm using a vintage 465B oscilloscope that's hooked up to E and Q. The oscilloscope, as many of you probably know, shows you voltage over time, so longitudinal voltage. Now, for an analog scope like this, the event of interest needs to repeat. This is super simple for this because a clock repeats, because I'm setting the trigger on E here most likely, and it's triggering to keep the waveform solid on this. Sometimes if the signal doesn't repeat, realize that you can use software in your system to make the event repeat. So you could start write a basic loop or an assembly language loop that makes the event of interest go on here. Now, what's interesting is what I've got hooked up here is to the E line here. It's showing that this is 894, I think, is this kilohertz. So 894 kilohertz, and that's the clock thing. Also, I did want to mention, let's have some audience participation here. Who knows what Q might stand for? If we look at that clock signal, it's 90 degrees out of phase with E. Any hams out there that know what that is? Yep. Yes, Q for quadrature. It's a 90 degrees out of phase with the main clock. So otherwise, it's exactly the same. So this is pretty good. It's showing pretty much what the clock should be on the Coco. So now let's switch to a logic analyzer. I have an older Saley 8-channel logic analyzer. It uses a nice. This is on a Linux machine here that this is showing the UI for, but it has a nice Mac, Windows, or Linux UI. Very good, and it can help kind of. Get into the digital circuit, but we're going to lose a ton of detail here. There's lots of probes and there's complex triggering here. I'm going to talk a lot about triggering, but you really just get a 1 or a 0. There's a threshold that it moves from 1 to 0. So if I go back to the oscilloscope, you can see there's a lot of electrical detail on that trace on those clocks. But if you go to the logic analyzer, it looks like it does in the the tech book, the clock goes up and down, nice square wave and that sort of thing. So I'm going to note here that try to get a logic analyzer that can set this voltage threshold level. This Saley is old and I can't do that. My Rigol allows me to set the voltage that is 1 and below that is 0, and we'll see this can go wrong. So slight beware here. So. All right, so that's kind of a quick introduction. We're going to do some more examples, but I did want to mention this is really recent stuff, history of the logic analyzer. So in 1973, the logic analyzer was invented to keep pace with digital technology. Digital systems required more inputs than the oscilloscopes accommodated. 4 channels is even common today, but back then a lot of them, like that 465B I was using, only had 2. The HP 5000A was the first logic analyzer. And you can sort of see I've got 2 pictures of it. I've got somebody had an animated GIF out there. I've got the links to these pages on the history of this, but it's kind of more like a blinking lights thing. And in fact, these older ones, what they really focused on was triggering. So you could set like high and low or this, that, and then they really expected you would take a signal out of this logic analyzer and hook it up to the external line on your oscilloscope, and you'd actually be probing around your circuit with an oscilloscope, not seeing it, because obviously this is not longitudinal here. It's like showing you the lights on and off, that sort of thing. So logic analyzers are great for debugging digital systems. They can trace many signals at a time and correlate them in time, and you can make measurements with really challenging triggering requirements. So we'll talk about that in some of the examples. In 2012, the mixed signal oscilloscopes, MSO, appeared, and these include logic analysis in with the oscilloscope. That's like, I have a Rigol that's the setup, so we'll get to see that. They're able to display, compare, and trigger both analog and digital signals. This is kind of handy because in addition to seeing the logic analyzer, you still have 4 scope probes that you can take 1 or 2 and poke them around the signal and see what the analog situation is at the same time you're looking at the digital, and it can be very nice. So we'll get to see that. All right, so I've talked about this a little bit, but one thing that's critical to understand here is that the logic analyzer is showing an abstraction of that signal. In the Coco example, we saw that the analog signal was much richer than the digital, logic analyzer one, because we're doing that. So it's making an educated guess what is low and what is high. And this can be pretty complicated. I've copied this diagram out of the first edition of Horowitz and Hill's Art of Electronics. And we're familiar with TTL, but we kind of think of it as, oh, it's 0 volts high, low, and 5 volts is high, and that's not really what's going on. This is sort of showing the low and high ranges and where the middle is and this sort of thing. We can see it for ECL, and CMOS actually looks a little more like we would expect. TTL is a little odd because you sort of say, oh, high is like 3.2 volts. That's interesting. It is, you know, CMOS with 12 volts, so they go through some of these. But this is what I was talking about, that this is what's going on down at the electrical level, and if you're working with a logic analyzer, you want to be aware of this, because if you're looking at TTL, you don't want these things set the same as they would be for CMOS and things like that. So you have to be aware of what you're looking at, and this is where the oscilloscope can be helpful. So the big warning is, if you remember nothing else, is that the logic analyzer can be wrong, and I'll show some examples of there. All right, so in fact, let's kick right into that example. How am I doing on time? Good, I'm doing great. Checking the Model 1 A key press as seen on the bus. So the Model 1, TRS-80 Model 1 has a pretty simple keyboard. It's like a grid, and inside that there's various logic that can tell whether the switch is things, but it's actually pulled in software on the bus. So we're going to look at this at the bus level. So the things we're going to be interested in is the Model 1 keyboard connector. So when you're looking at it, keyboard star, which is low, I'm using the star for when it's actually, when it's low value, that's when it's active. It's low when scanning. And when A0 is at 5, it selects row A. The row A is in. So we're going to be looking at A0. Oh, sorry, this is the connector pins. So keyboard is at pin 14 on the connector, A0 is on 5. D is the output, that's at pin 16, and it indicates that an A is being pushed. So we're not going to see what's going on inside that. That's the tri-state stuff. But you might do this if, you know, to motivate this. Why would you hook this up? If you're debugging a key, and you're like hooking up your multimeter, and when you press the key, it's beeping, like it actually is connecting, but the computer can't see it, then maybe there's something wrong in the logic, and this would be kind of your next step. So if the Model 1 doesn't register it. So I'm going to start with this example with the logic analyzer, and then we're going to go back to the oscilloscope, because I want to illustrate this gets kind of complicated, even though it's pretty simple on the oscilloscope. So first thing we're going to do is hook up the probes. So you can see I've got the connector into A0, keyboard star, and D1. There's also one more connector, which is absolutely critical. Don't forget to hook up your ground connection. That'll really ruin your day fast. You get all kinds of crazy stuff that you'll be like wondering what's going on. Is your computer completely blind? This is you can see this a little bit from far. That's a Model 1 system board. And I've just got, connectors with a cable going over to the keyboard, the Model 1 keyboard. So this is a simple Model 1. So what we can see here is I haven't, in this particular trace here, each of the signals I have hooked up shows up as a channel. Now, I've been easily able to annotate those. So the digital lines I've got, this is the SAILI I'm doing this with. I can type in, because this is fully on a keyboard, so you can easily type in like keyboard star A0 D1, so it's really easy to look at those. You're going to notice when I do this with the Rigol, I don't do that because it's a giant pain in the neck to type these things in on the interface there. So if I cycle in on where I triggered, you can see the T up at the top. You can see that keyboard goes to low and A0 is high. So if we were pressing the A key, which we aren't, we would expect D1 to be high, but it's not. So we're not pressing the pull from the software. This thing triggers and we end up with low, high, and in this case, because I'm not holding the A key down, it's going to be low. So stops it immediately. If I say go capture, this triggers immediately on a Model 1 and stops. We get a thing right away. So if I want to do the A, I simply expand the logic analyzer trigger to include D1. And what we want to see is D1 go high. That would mean it registered the A being pressed. So if I did this, I would hit go on the logic analyzer and it would just sit there because the trigger hasn't happened. When I push the A key on the Model 1, boom, it would show this capture, and we would see keyboard is low, A0 is high. I'm pulling that row on the keyboard, and I'd actually see D1 as high. So this would be good. Where you'd realize you might have a problem in the logic is if you're holding that A key down and you do this and it never triggers. There might be some problem with the logic. And it runs until A is pressed. So Now let's switch to the oscilloscope to sort of illustrate the issues with this. With the Tech, I'm going to go back. I love the Tech 465B. It's a great old scope. We only have 2 channels, but we sort of have 3. We have an external line as well that we can trigger off of. And in fact, the 465B is kind of interesting because you can actually show the external trigger on the screen by pushing a button. It's neat. So we can trigger on any one of them, but we only have 3. So I'm going to trigger on keyboard, the keyboard signal going low. So let's start with that, and then we'll switch over to the Rigol. We'll do the Rigol. We'll try both, but let's start with the Tech 465B. So again, this is my setup here. Excuse my poor, ruler ground. It's got a metal ruler I'm hooking all the oscilloscope probes up to, and I've got D1 on probe 1 is on keyboard star, and then probe 2 is on D1, and A0 is the external line. All right, so this is what I see. I'm not pressing A here on the keyboard. This is what I get. So I'm setting the scope at 2 volts per division here and half a millisecond per division. So you can see keyboard go low and D1 is low because we haven't pressed the A. Now, let's now press the A. I'm holding down the A. And this is interesting because I do see the high line, but I'm also seeing the low line. So what the heck is going on here? Well, this makes sense, but this is where the difference between what the logic analyzer was showing you and what the oscilloscope is. 8 scans are done for each of the rows that are there. So, but only 1 has the A. So this is a little tricky to see, but if you look at where I've circled in yellow, when the A is pressed, that particular trace is fainter. It's much more noticeable if you saw this on the scope than the one below it, because it's drawing that lower one 7 times for every 1 time it draws the A on there. So this makes sense. And you can use the scope to do this, but you have to understand what's going on a lot deeper than the logic analyzer. You could set the complex trigger and you saw what you expected. This one I have to sort of understand what's happening inside the Model 1 and do it. Now what I've done is I got an animated thing where I'm pushing the A key. I'm kind of holding it down, letting it up, holding it down, letting it up, holding it down, letting it up. So you can sort of see like what you might see on the 465B. And like I said, it's hard on this because of the camera to see, but the line that's popping into existence with the A is far fainter than the other one. So that's great. This is how you might have done it if you were like, in fact, this particular scope, the 465, is what Steve Wozniak used to develop the Apple II. So it's kind of, the same time frame as our Model 1 was developed. Now let's go to something quite a bit more modern, the Rigol MSO 5000, which I have is a 100 megahertz 4-channel scope with a logic analyzer from about 2018. We can do a lot better on this. It has pattern triggers on the probes, so this allows us to lay out more complex oscilloscope triggers than we're able to do on like the Tech 465B. This is a little bit tricky to do with the logic probes. It has a software-driven hold-off, and I had to play with that. I used a very long time, 9 seconds to get this to work, but that's kind of whatever your modern scope has. It might work, it might not. So again, hooking it up is pretty much the same, but I'm only going to hook up, I've got the 3 probes now because I've got four probes, I've been 4 channels on this modern scope as opposed to 2. So here's what we end up with. You can see I've got the 4 channels at the bottom here. I'm at the bottom right. The 4 channels are plugged into the scope. The colors match up with the things there. So keyboard star is at the top. Then I believe it's, which one did I put next? Probe 2 is D1, which is actually at the bottom, not confusingly. The D0 is, hang on, sorry. I'm going the wrong way. D0 is on probe 2, which we want to, probe 2. So the blue signal is the one we care about at the bottom. That's the data coming in. So we can actually trigger, we're gonna go drill into this, but that circled box at the bottom of the screen is the actual pattern trigger. And I'm circling in on the event when we are doing the thing there. So I'm also circling so you can see that this scope has an input. We're gonna get to this, the 16 logic channel analyzer channels. All right, so drilling in here, we're able to set that what we want is channel on the first probe, we want it to be low. Then we want the A0 line to be high and the D line, the output data line to be high as well. And in fact, that's what we're seeing. So we're getting something very similar to the logic analyzer. We're not getting that like overdraw where most of the time it's low, but some of the time it's high. So this would sit there if I had it on normal mode, and when I press the A, it would actually trigger, again, like the logic analyzer did. There is an auto mode where it might just draw a trace. A lot of times that's set so it won't just leave the screen blank on the oscilloscope. The logic analyzer, the SAILI doesn't really have that per se. Okay, so summary of this part. Oscilloscopes and logic analyzers, they can help you with your TRS-80. Analog scopes are a challenge, but they are kind of retro, so it's kind of fun. I do like my 465B. The SAILI into the PC gives you gigabytes of memory and a nice interface. So it can store a whole lot of lengthy traces and things like that. So it is really, really nice. But in the modern oscilloscopes combine the analog and digital capabilities, which also can be beneficial. So my advice with kind of doing this, if you have one of these, is don't wait to use your scope or analyzer to your TRS-80 breaks. That's like a terrible plan. You want to spend a lot of time with this on actual working computers so you understand what these signals are supposed to look like. If you're sitting with a broken Model 1 and that's your first attempt at using an oscilloscope, that's like really bad. It's going to be a bad day. So like spend a lot of time on your system of choice, whether it's a Coco or a Model 2 or or whatever it is, dig into it. Put in tons of time learning these tools on your Coco and Model 1. They're kind of like very useful if you have them. I've also found, because I'm not a professional in any way for a EE, mostly I write software, it's kind of fun. You kind of dig, learn some things and dig into the electronics a little bit and learn kind of more about the electronics that make these systems go. Also, finally, a safety advice. I've got my remember kids, electricity will kill you. Be safe with the computers, know where the high voltage stuff is, and be careful, wear gloves or things like that. Big things like that. And I spent a bit of time, just a caution on the oscilloscope. Most oscilloscopes are wall ground or earth ground, so you don't want to be poking that around, they're like super high voltage stuff without knowing what you're doing. If you're poking around a TTL chip, that's probably okay. All right, so getting to a more realistic example, let's do something where we're actually looking at a sort of a bus-ish type thing. So this is the last example I'll go through. The Model 1 memory write cycle. So first off, this is right out of the Model 1 technical manual. The clock on pin 3 is 10.6 megahertz, so we'll kind of look for that. And then what happens is MREC not on pin 19 goes low. So this is a memory request line. It goes low, and then shortly thereafter, write goes low. So that indicates we want a memory request and we're going to do a write. Now, MREC, which is confusingly named MREC because it has nothing to do with MREC not, and we'll see that in the diagram, goes high after a certain time. Then we have an interesting thing going on here. The next couple of lines, next, QMUX, and QCAS, they go high, high, and low at the rising edge of the clock on the next clock moving up. And we'll see how in the schematic that ends up happening. On the rising edge of the next three things. And we notice down at the J there, RAS mirrors MREC not. So that's very similar. So this is an interesting one to kind of see. This is starting to get into like where we certainly don't have enough scope probes to start looking at all of this. So the logic analyzer comes into play a little bit. So what's going on in the schematic? We can see on the CPU, the right line and the read line, and we can see IMREC not up the very top. And in fact, we can see why, we can see why the IMREC not is coming out of the CPU, but the IMREC line is actually a negated OR from the write and the read. So that explains why it's there. A little bit different, but that's what they call it. Now, how did that do next QMUX and QCAS, which I'm showing over at the left? How did that go clock edge after clock edge after clock edge? So there's actually a series of flip-flops in the schematic that are used to kind of move this along, and you can see it inside the 74 LS74. I thought I read that wrong. But those kind of are chained together, and they end up causing the, rising, falling of next QMUX and QCAS. So to hook this up, let's go back to the SAILI. We've got a kind of, now we're starting to look, this is what things look like when you're using a logic analyzer. You've got a whole bunch of things connected all over the Model 1 motherboard. You can see some over on the CPU on the right, and then others over on the flip-flop and chip, the 74, LS74. So kind of all over the place. And you really need the schematic to be able to figure out where you're going here. And this is what the setup of this is kind of like. So I have the Model 1 kind of splayed out. The keyboard's on the right, the motherboard's on the left. It's plugged in to, this one's a USB powered Model 1. I'll have this exact board will be demoed at my table if you want to see it. And then over with the SAILI, you can see the little SAILI box right above the Model 1. It's a little red box right here, and it hooks into the PC, the Lenovo laptop here under Linux, and you can see the UI I've been showing screenshots of is right there. So you sort of use your laptop to kind of work with the SAILI logic analyzer. This is kind of a nice setup. So what do we see? We can see that this is kind of like, it does start to look like the things. Again, we can nicely type in whatever we want over on the left-hand side, so we can see A, B, C, D, E, F, H, J, like we can on the other diagram. I've typed all that. And everything looks pretty good. One interesting thing is the clock looks odd. That doesn't look right. And in fact, I mentioned that this is an abstraction, so this is a great example of this. The SAILI is getting it wrong here. So the error is due to sampling and voltage range. Remember, the logic analyzer is showing an abstraction. And I cannot change on this particular old SAILI what that voltage divide is. So that's definitely a feature you'd want if you got one of these, but it's not possible, so I'm kind of stuck with this kind of abstraction. So I'd expect it to be 10.64 megahertz, and it's showing something like 1.78 megahertz. It's not right. It's not right. And you can sort of see this is kind of showing the trace on the logic analyzer versus the actual one from the book. Now, this one's pretty good. I will caution you, sometimes your documentation can be wrong. So don't always believe I've got some error with my logic analyzer that's not giving me what was in the tech manual. It's quite possible that you're dealing with this. So I was talking to Boise, trust but verify the documentation. It looks like this documentation is correct though, other than the clock is coming out weird, but we'll talk about why. So the Rigol I mentioned has the Rigol MSO 5104 scope has a logic analyzer. So we're actually going to use that, not the oscilloscope probes. Again, this is what it looks like. I've hooked up the Rigol to the motherboard. And here's what you end up with in this particular case on your desk. You have all the signals. They're going into this, the same place the SAILI was. I've got this block that runs a ribbon cable into the oscilloscope, and we manage things on the oscilloscope, not a PC laptop. So that's kind of different than the thing. So Fixing the clock. Now here I am using the Rigol analog and digital. So I'm using probe 1 on the oscilloscope plus a digital signal on the logic analyzer, and I can fix the clock. So I'm seeing the logic analyzer's view of the clock at the top, and I'm seeing the actual oscilloscope probe at the bottom. This can be really handy to do on these sorts of things. This is one of the advantages of this kind of setup. And in fact, we can adjust that. What I ended up doing to get that to come out right was I adjusted the threshold on D0 through D7 in the logic analyzer to 1 volt rather than 1.4 volts, and that seemed to help it in this particular case, given its TTL. As I said before, my Saley can't do this because I can't adjust the line, so that's good. And with the cursors, kind of using the signals, I was able to measure this at, I expected 10.66, I got 10.58. So we're pretty close on the Model 1 there. So this is looking a little bit better. All right, so here we go. We can actually set up the trigger to trigger on the memory write cycle. One of the things you'll notice, I've got the little arrow over to the left. I don't tend to put in all the text on this thing because it's a giant pain in the neck to poke this in with the screen. So I don't know if you can hook a keyboard up and do something fancy. I haven't tried that, but that would be sure nice. The laptop is super nice for that because it's super easy to click on something and type in the name of the signal. It is a giant pain on the oscilloscope to poke the signal and then go into the little thing that's like your cell phone and so you know, these are going to be kind of things, but we'll see the things. So we can see the traces look about right in our example here. So we've got the Rigol is showing the memory write kind of as we'd expect, which is great. And I did want to talk about this. In the Saley on the laptop or on any PC computer, you can sort of run it and it's like trailing off remembering the trace in memory that you had. So you can have it kind of zoomed up and it'll be great. It'll go and then you still have like 2 minutes of these traces sitting in memory and you can scroll back and zoom in and zoom out. This is super great. This is a little less obvious on the oscilloscope. To use the deep memory, what you need to do is when you set up your trigger, you want to zoom way out in time. Then press the thing to go, collect a trace that triggers, and it'll not be readable, but you then have that entire caption, like maybe it's a half a second or a couple seconds or something. And now, because it has put those in memory, you can scroll around that trace, zoom in, zoom out around that sort of thing. This is a feature called deep memory in these scopes. A lot of them have, you know, reason for, especially for the logic analyzers, they have a lot of memory. But it can be very useful, but it's not as obvious to understand how it's being used here. So I just wanted to mention that. So zoom way out, you can see I zoomed way out, captured a whole lot of, you can see a lot of memory things going on here. But the one that the trigger triggered on is the write, because I set up the trigger to do that. How did I do that? I used the pattern trigger again, and you can see on the digital signals, X means don't care. So on the clock, I don't care. I want 0 on the memory request low, so I want that to be low, and then I want the write request to be low. So those are the two things I'm triggering in, and then the rest of them I don't care, and you can see I'm not using the analog signals. So those are, you could trigger on all of them combined, which is an advantage of this, but the pattern trigger works similar to the way we did it on the Saley. All right. So I'll start wrapping up and then we can have some questions. So I think we've introduced the logic analyzer with some simple examples, and I spent a lot of time on contrasting it to the oscilloscope. So again, you don't always need this. Now that we've seen it, I think talking just a little bit about if you're trying to understand a bus or expand something in a bus that's more complex, this is a great tool to help you understand what's really going on. Verify the documentation, trust it, but verify, and then really deeply understand. More channels is better. Sometimes an oscilloscope can be somewhat limiting if you're trying to understand like a whole bunch of data lines and address lines and what they're doing and all the control lines at the same time. This is definitely not the first test equipment you should have. You know, if you're fixing things, oscilloscope is way more useful than a logic analyzer. And as you've seen, the kind of examples I did were kind of trivial, but you can sort of see even at the end when we were doing the memory write cycle, you're starting to get like a rat's nest on that Model 1 board. You know, think about that with like 64 probes hooked into something. So it can be really good. But you, like I said, you learn, start simple and build up your knowledge. You will understand kind of what you're working on as you work on it over time. You don't start a project and hook up, 128 things. You start with a couple and, then add more and more and more and more as your, mental theory of what's going on and your understanding progress. All right, questions? Yes?
What kind of sample rate do you look at for something like this? I mean, like a 24 megahertz or?
That's a good question.
Repeat the question.
Yes. What kind of sample rate do you look for in something like this? I believe the SAILI I have is like 1 gigahertz to 2. But again, these are a little bit dicey because they tend to put these in the like write up about the analyzer where it's like if you use one digital signal, you get 2 gigahertz, and then when you add a second one, it's like drops down to 1 gigahertz and drops down to like, so you really have to be careful and read like if you use all of the channels, what is the sampling rate. However, I don't think the sampling rate, like I said, I've run into far more problems with the making sure you have the voltage set right, because a lot of these things assume you're using like CMOS circuits, so we're oftentimes touching TTL, so you want that voltage a little bit lower, that voltage divide, and you want to make sure you can change that. That's where I've run into problems. The sampling rate has been less of one. Although I will mention one case where I did run into that. The SAILI can show the not only the digital traces, but it can show the analog ones. And the sampling rate is so bad on the SAILI that those analog ones are oftentimes useless, even on a TRS-80. So if you had a faster sampling rate, it would be better. It would be better. The Rigol is very, very fast. For all the channels, it's well over a gigasample. I haven't had any issues with that. So I don't know if that helps, but again, we're kind of working on like 1970s and 80s technology. So a lot of the stuff, even on the lower end, is good enough, provided you take a look at it. But, Oh, yes.
Logic analyzers are very, very expensive, perhaps out of range of the casual hobbyist who doesn't want to spend their entire life savings on such a tool. Do you have any recommendations as to an inexpensive solution for that?
I do not. I think like that's actually logic analyzers are expensive. They're well out of the realm of hobbyists sometimes, so you could spend your life savings on them. So I have a couple ideas, but I think this is a good topic of conversation. The SAILI that I have, which has got some serious flaws with only 8 channels and issues, it's also 8 years old, was about $200, $300. I think you can get a discount if you're a hobbyist from them. But a decent one from them, a 16 channel with a lot higher sampling rate, is nearly $2,000. So this is pretty expensive. The Rigol that I'm using is roughly about the same price. That's why kind of like it's nice to have the entire scope with the logic analyzer things. I think if you go into Rigol's current stuff, you can get something with a logic analyzer probably around $1,400. But this stuff is, yes, it's getting very expensive. I don't know. Do you have any suggestions, Lee, of like?
I haven't used it very much, and the software is pretty damn janky. But I have a digital discovery. It's a USB module that attaches to your computer. It's 5-volt tolerant.
Yep.
I think it's got, 32 digital inputs or something like that. But they're not like high voltage protected like real equipment is or anything, so you can blow them up if you're not careful with it. I understand. But I mean, for somebody, just goofing around like me, I think they're $150 or something like that.
Yep.
They're pretty crappy, but it's.
What was it called? Digital
Digital discovery.
Okay, so Lee found digital discovery to be useful.
It's not professional grade by
Yeah.
any means.
So not professional grade and definitely not protected, but probably fine for poking around like 5-volt TTL kind of stuff. And that was more around $150. So that's worth checking out. So I think like lots of there's lots of things. Like I said, this is not everybody needs one of these, but if you're trying to figure out how would I add something to the bus and you can't figure out what the bus is doing, this is probably the tool you're looking for. Another question.
So the bus pirate is not too bad. It is very inexpensive. So
Okay, so the bus pirate is not too bad.
Pirate, yeah, they got multiple versions of it. And there's modern software that has like a logic analyzer mode. You can do a heck of a lot more than just logic analyze. And one other thing is,
So the bus pirate is, it's got logic analyzer mode, but it's got other features as well. How much does one of these cost?
I mean, the cheapest ones on eBay are probably $20 or 20.
Oh, 20 bucks on eBay. So these are good. Okay. I'm guessing this does not have good quality voltage protections either. This is probably similar to Lee's.
I think I haven't used them, but I have seen them out there and seen the development of the software mature.
Okay.
We're up to like version 6 or something now of this, and so
Yep.
it's pretty mature.
So the bus pirate has, they're still working on the software, but it's maturing a bit. So that sounds like a very low cost thing that you could try out. So interesting. Yeah.
Yeah, I kind of want to add along this line,
Yep.
the thing with this single analyzer, the low-cost ones would be very good if you're designing peripherals for them. You already signal you want to test your output, okay? And because the rate's going to be low enough. The thing about the bus pirates is they can support certain protocols, okay?
Got it, yep.
If using that, and again, it costed less for the whole machine than probably what the protection circuitry, and the high-cost one cost. And so, sometimes it might be a throwaway if you blow it compared to
Sure.
others. So there's a use for it for the hobbyist, but as far as to analyze it to the level that you're doing for, yeah, probably not the bus prior. But whereas hobbyists who just play with some of the things, we want to look at the signal, okay, is it giving out what I'm doing? I'm programming, an interface to something, is it doing that? It's probably going to be good enough for those type of things, but not for, what you discussed here.
Yeah, I mean, that sounds great. Just kind of more discussion that this might be helpful to the hobbyist. These are, like I said, I kind of have these, so I don't know, maybe more money than sense, but the thing there. But I've not tried that, so the bus pirate is one to take a look at. Also, I should mention, I didn't show this, but of course, both of the Saley and the Rigol have, very serial bus decoding and various things as well. So that's pretty much, most of these are going to have that built in these days. I've used it. In fact, last year, if you remember, my demo was showing TRS-80 GP going through real serial ports to real terminals. And in fact, I used both of these logic analyzers quite a bit. In fact, sometimes both at the same time, hooked up to 2 serial lines decoding the RS-232 to see what was going on. So they can be useful for that. And that's super slow. You don't need anything super sophisticated if you're doing that kind of stuff. Certainly not.
Not something like the bus prior would do very well at.
Yep, sounds good. So I think, go ahead, Paul.
I was going to say, if you're wanting to make this stuff up, you can find a lot of vintage HP 16XX series or 1650s or giveaways, 60s, $100 range, 70s or $200 to $500 range. But you can get into it if you're willing to spend between $100 and $500. You can get a big step up and become much more.
Yeah, that's a great point. Paul's making. I'll repeat this, but I've showed my vintage oscilloscopes. You can get into the vintage HP logic analyzers that are great devices. When I was in my master's program in the early 90s, we had these devices and they probably cost more than my car, but now you can get the HP logic analyzers for a couple $100. If you're willing to spend $100 to $500 and get a vintage one that's very capable, even compared to these things I'm talking about. So that's another great hobbyist way, especially if you're into the vintage stuff.
Yeah, I'd say start at the HP 16.7Xs and move up.
HP 16.7Xs and move up.
The 60s, they're not fast. The 70s, they're about 2 nanoseconds, so 500
That's pretty fast.
And those actually have a lot of extra things such as state analysis. You can go up to 132 channels on scope, or on a logic analyzer at a time. They're very capable machines.
Yeah, super.
Post on the Discord.
Yeah, folks will help you out.
Anybody interested, post on the Discord.
Yeah, post, that's a good, if you're interested in this, post on the Discord, and people they'll have lots of ideas. If you're wanting to go the $20 route or go the vintage route with an HP or look at a MSO scope. There's people have opinions on those. Any other questions? I think it's time for the break. All right. Well, thank you. I'm glad to open Tandy Assembly, and everyone have a great weekend. Enjoy the